A ball thrown in the air has a velocity v of t equals 100 minus 32 t feet per second at time t seconds. Find the total displacement of the ball between time t equals 1 second and t equals 7 seconds. The velocity is given. We know that the velocity is the derivative of the position function. The displacement is computed using the s of b minus s of a. The displacement is the change in the position, the ending position minus the beginning position, in this case from t equals 1 to t equals 7. Since the velocity is the derivative of the position function, to find the displacement or the change in the position, we integrate the velocity. The variable of integration is t. We will integrate v of t dt from t equals 1 to t equals 7. This will give us the displacement. The integral from 1 to 7 of 100 minus 32t dt can be computed using either the Riemann sum or geometry. Since the integrand is a linear function, we will use geometry instead of the Riemann sum. First, we graph the integrand. This is the velocity function. The graph of this linear function is a line, not drawn to scale here. The y-intercept or the v-intercept is when t equals 0. When t equals 0, v is 100. The t-intercept can be computed by letting 100 minus 32t equals 0. Solving for t, we get t equals 3.125. And so the t-intercept is 3.125. However, we integrate from t equals 1, again not drawn to scale, to t equals 7. And so we are also interested in the velocity when t equals 1. If we plugged 1 into the velocity function, we will see that v of 1 equals 68. So the height is 68. And we plugged 7 into the velocity function, we will see that the height is negative 124. The definite integral is now the sum of the two areas of these two triangles. The first triangle has the area of 1/2. The base is 3.125 minus 1 times the height. The height is 68. The second triangle has an area of 1/2. The base is 7 minus 3.125 times the height, but the height is negative 124. Evaluating these areas, we see that the first area is 72.25 and the second area is negative 240.25. And again, the picture is not drawn to scale here. The integral is therefore the net area, or simply A1 plus A2, where A1 is 72.25 and A2 is negative 240.25, and we will get negative 168. The unit is in feet. And so we just computed the integral, and we saw that the integral of the velocity from 1 to 7, where the velocity is 100 minus 32t dt equals 72.25 minus 240.25, and that will give a negative 168 feet using geometry. Alternatively, we will first find an antiderivative of the velocity. This means that we will find an antiderivative, or the indefinite integral of 100 minus 32t dt. There are two terms in this indefinite integral. The first term is 100. The antiderivative of 100 with respect to t is 100t. minus 32 is a constant multiple. The antiderivative of t is t squared over 2 using the power rule. And don't forget a plus c, a constant of integration. Simplifying this, we have 100t minus 16t squared plus c. This is the position function. Remember that the displacement is the change in the position, so we will evaluate s of 7 and s of 1. S of 7 is 100 times 7 minus 16 times 7 squared plus c. This is negative 84 plus c. We will take care of this c later. S of 7 is the position of the object 7 seconds after. S of 1 is 100 times 1 minus 16 times 1 squared plus c. This is positive 84 plus c. The displacement is the change in the position, or S of 7 minus S of 1. But S of 7 is negative 84 plus c minus S of 1 is 84 plus c. Since c appears in both expressions for S of 7 and S of 1, we didn't really have to write c because c will cancel out. The result is negative 84 minus 84, or negative 168, the unit feet. And so we get the same answer.